All right, so number of things I want to go over today. I'm not going to go into the stuff that we started talking about Thursday, which was memory circuits and circuits that have a notion of what state they're in, what's happened to them in the past. I'm going to push that off to probably Thursday. What I want to do today is talk a lot about circuit design. Okay. The stuff that you were doing in Lab 2 and the stuff you're going to have to do in Lab 3. And I want to do, among other things, a start to finish example of designing a circuit all the way from problem definition to a full wiring diagram. And I won't put it in Tinkercad because I think people are having good success with Tinkercad. But I want to go through the steps in between. I want to talk about Lab 2. I want to talk about Homework 2. And then I want to run through the guidelines for Lab 3, look at Homework 3, and there will be some new material I want to get to hopefully today, which will be basically talking about two things, multiplexers and demultiplexers, okay? And these are coming from Chapter 3 and Chapter 9. So if you want to look ahead to stuff we don't get to today, Chapter 3 and Chapter 9. Now we're not doing all of Chapter 3, and if you look at the homework assignment, you can see which questions we're skipping. In particular, compressed truth tables, compressed K-maps, I'm not going over right now. We may come back to them. But we will talk about decoders and demultiplexers, encoders, multiplexers, and we've already talked about programmable devices, which is the other part of the chapter. So let me start. So first of all, are there any questions? I haven't had anybody coming to office hours, so I'm kind of taking that to mean there's no questions. But if you have questions, go ahead and put them out there right now, and we can talk about them in class. Otherwise, I will jump into some of this stuff. All right, well, let me start with the homework. So homework 2. I decided to grade question 7. So this was a K-map question. And it asked you to, for the following functions, find a minimum sum of products. Okay. And the functions were given to us in this compact form. So let me write this down for the first one. And then I'll switch over to my camera view. Alright, so it's asking us to find a minimum sum of products using a K-map for this expression. So if you were to write this out as a truth table, first of all, it's PQRS, so you can't switch back over to ABCD because we don't know what those mean. So whatever the function's arguments are that are specified here, that's the value you need to put, the headings you need to put in your truth table. And I don't think I need to fill in all of these. So if we put these in the right order so that these numerically form the numbers 0, 1, 2, 3, 4, 5, 6, 7, and so on, then this is minterm 0. This is minterms 2 and 3, 4, 5, 6, 7. I guess I will finish filling this out. Okay, so 8, 9, 10, 11, and then all of these are 0. So if we make our usual K-map, and almost everybody did this the way I've been doing it in class, which is if our function is PQRS, they're labeling these PQRS. You're not required to do that, right? You can put any ordering that you want on here, but I am always going to do this as follows. And if you're writing your elements down in, say, PQRS or SRQP, it's another step of translation you have to go through when you're looking at your notes from what I've done in class and you're looking at what you've done. So consistency helps, right? So we want a 1 in this case where PQRS are all 0, so that's a 1 right there. PQ are 0, but RS is 1, 0. That's a 1 right here. And 0, 0, 1, 1 is right here. And these next two ones, P and Q, should be 0, 1. And again, RS should be 1, 0 or 1, 1. So that's those two ones. And then these two ones correspond to PQ are 1 and 0. And then again, RS are 1, 0 or 1, 1. So there's the ones that we get. But remember, after you've done this a few times, you're welcome to observe and use the following trick, which is, regardless of where the ones and zeros are, if I know that this is minterm 0, 1, 2, 3, 4, 5, 6, 7, I can fill in this table once, and it will end up looking like this. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I don't want you to just blindly use that. I want it to make sense to you. And until it makes sense to you, stick with this, right? Take the one, look at the values of PQ or RS, find out which box that is and fill it in. But come back to this and see if this makes sense. And if it does, it's a very direct way of filling in a K-map from a compact form. Because 0, 2, 3, that means this box, this box, this box. That's those three ones. 6, 7 means this box, that's those two ones. And then 10, 11 means these two bottom boxes, that's those two ones. And you don't need to do any of the truth table stuff. Okay, so you know, in a testing environment, for example, or if you're doing 50 of these problems, right, you can go directly from here to here. All right, so most people got a good collection of ones here. A few people missed a one. A few people put these two in this row instead of this one, and I think they were trying to do something like this, but they were just coming down sequentially. Remember, you go 0 through 3, 4 through 6, 4 through 7, and then 8 through 11 jump down to the bottom, and then 12 through 15 in the middle. Alright, so covering with rectangles, this was the part that most people lost a few points on. So this is pretty obviously a 2x2 rectangle, okay? We could do it as a pair of 2x1s or 1x2s or 4 1x1s, but bigger rectangles, fewer rectangles, that's what we're after. So putting a big rectangle around here, that's definitely a way to go. Okay, this one over here is all by itself, but we can wrap, right? So that rectangle can wrap over to this rectangle, and we've got a 1x2, which is better than a 1x1. And then the third rectangle is these ones down here. And again, we can wrap those up to the two on top. And now we've got a 2x2 rectangle instead of a 1x2. And if you had ordered these things differently, right, this split 2x2 would have been somewhere in the middle, not split, right? So we're just wrapping around the ends to acknowledge that the order of these was effectively arbitrary. All right, so this 1x2 rectangle, which goes here and here, P is a 0, Q is a 0, R could be a 0 or a 1, S is a 0, so that's S bar. And this 2x2 rectangle, P is a 1, Q is a 0, and then R could be a 1, P is a 1 or a 0, so P doesn't matter. Q is a 0 in both of these. And then R is a 1 in both of these. And then S could be a 0 or a 1. So this is Q bar R. And then this upper 2x2, P is definitely a 0. Q can be 0 or 1. R is a 1. And S could be a 0 or a 1. So there you have your three terms, and then your final expression is just F equals the sum of those, P bar, Q bar, S bar, or P bar R, or Q bar R. All right, and then for the other one, 7B, you're covering, looks like this. Your ones come out in these locations, and that's an obvious 2x2, and that's an obvious 1x2, and this corner one you can pick up by overlapping with that. Remember, overlaps are perfectly legal, okay? If you overlap, that's fine. It will sometimes help you make a bigger rectangle. Just make sure you cover the ones, don't cover the zeros, and if there's dashes, you're allowed to cover them, but you don't have to. And if you have a don't care, put it in as a dash, not as an X. Okay, this is standard symbology, so make sure you do it the standard way so that other people looking at your work understand more easily what it is you're doing. Alright, so let me know if you have any questions about that or any of the other homework questions from Chapter 2. Alright, let's talk about Lab 2. Okay, so first of all, Lab 2, a bunch of people turned in late, so if you turned Lab 2 in on time, you got 10 bonus points. If you turned it in a little late, I did not take off points. Okay? So this doesn't penalize people who turned it in late, but it also does not penalize people who you know, did what they had to do to turn it in on time. You get 10 bonus points, so an extra 10%. And I don't usually do that, okay? But this is only the second lab, and I don't want people to start falling really far behind with, you know, heavy penalties for late work. So so going forward, right, try to get it turned in on time, even if it's not quite where you want it to be, okay? Because it's worth not getting the heavy point deductions. All right, so let's take a look at Lab 2 that you've already done and I've graded. All right, so experiment 1 is about LED usage. All right, so here's my first very important comment. Any time that you work with a circuit in a lab, if you're analyzing it, if you're discussing it, if you're building it, if you're testing it, you've got to have a circuit diagram, okay? This is a circuit diagram. It's got logic symbols, it's got symbols for resistors, it's got a symbol for an LED, it's got power and ground, right? That's a logic diagram, okay? I'll call this a schematic diagram also. A picture of your Tinkercad circuit does not take the place of this. Now, if you want to put those pictures in, that's fine. They look cool, and sometimes it'll help me see, you know, where you switched an LED or something, right, if your circuit wasn't working. But you've absolutely got to have a circuit, because what are you doing? You're writing a report. You're going to publish this report for other people to see and say, you know, in configuration 1, the LED lit up. Well, somebody reading that is going to expect a picture like this. And if they get a picture from Tinkercad of a proto board with some wires and something that looks like an LED, right, they're not going to know how to interpret that, right? They can guess, they can map it from what they've done in Tinkercad, but this is standard symbolic notation. So you always, always, always need a schematic diagram, okay? Even if you're required to have a Tinkercad picture, got to have a schematic, okay? So that's the first thing. And any time that you're referring to, you know, this is what happened in configuration 3, make sure the person knows what configuration 3 is. Okay, so all 3 of these configurations, the LED should light up. So in the first one, we have 5 volts over here. It goes through a resistor which limits the current, but the voltage at this point of the LED is 5 volts. At this side, it's ground. Current flows from positive to negative, so current will flow through the LED and make it light up. And most people observed that, and most people explained it. Configuration 2, again, we went through this a few times. L means low, that's logic 0, which means ground. H is high, that's logic 1, which means VCC. So if you connect this end to ground, and this is an inverter, the output will be logic 1, which is 5 volts. And so again, we have 5 volts on this side of the LED, ground on this side, 0 volts. That's a positive voltage difference. Current will flow in this direction through the LED and it will light up. The third configuration is even weirder, right? We have a high input here, so a logic 1 going into an inverter. The inverter turns it to a 0 on the output. So this point right here is logic 0. That's ground. So at this point we have 0 volts. Over here we have 5 volts going through a resistor, going through an LED to ground. The LED will light up. Right? If you have 5 volts here and 0 there, current will flow from the 5 to the 0, which goes through the LED in the forward direction. The LED lights up. So it should light in all 3 configurations. Okay, and so you'd like to have a picture of these and say, you know, in configuration 2 the LED lit up, but it wasn't as bright as configuration 1. In configuration 3 it didn't light up, but it seemed like it should, so we checked the wiring and the chip wasn't connected correctly, and when we did that it lit up about as bright as configuration 2. Or whatever, okay? Alright, so that's experiment 1. Experiment 2, again, we've got a circuit, got to have the circuit diagram in there. And we have a switch, and we're telling you what a 0 and a 1 mean. 0 means the switch is closed, 1 means it's open in the position it's shown. We have 2 lights, and a 0 means that they're off, and 1 means that they're on. And your goal was to build this circuit and construct a truth table. Okay? Your truth table needs to have 1 input, labeled switch, and 2 outputs, probably labeled L1 and L2. And for the switch closed, you should show what the 2 values of the output are, and for the switch open, you should show the values of the output. Okay, so let's analyze this circuit. And I should have printed this out, but I didn't. And I don't have a way to annotate it here. So, this switch is, let's just look at it right now. It's in the open position. Okay, so let's start a truth table. So here's our switch, here's L1, here's L2. The switch is open, that's what we're calling a logic 1. So we're going to fill in this row on the bottom, logic 1. Okay, if it's open, this point is not being pulled to ground, so this goes through 5 volts, through a resistor up to 5 volts. This is a logic 1. Inverter turns it into a logic 0. So this point right here, this junction is 0. Okay, it's ground. Well, if this is ground and this is ground, there's no current flowing through the resistor. L2 is off. So this is a 0. And again, if this point is ground, it goes through an inverter. This will be 5 volts on this end. The other end of the LED is also 5 volts. 5 volts, 5 volts, no current. Current flows from a potential difference, right? So if you have 5 volts on both ends, no current flows. L1 is off. So this is a 0. Okay, now imagine that we close this switch and we're told closed is a logic 0. So we're going to fill in this top row of our truth table. And it's logic 0, right, because this point is now at ground potential, right? If we close this switch, this point's pulled to ground, it's 0 volts. Well, 0 volts goes through an inverter, so this junction right here is 5 volts. Well, 5 volts through an LED to ground, that's going to turn L2 on. So L2 will be lit. And 5 volts through another inverter goes to 0 volts. And so now we've got an LED, 5 volts over here, 0 volts there, current flows in that direction. The LED turns on, L1 should be lit. So this is the truth table you should have in your lab report, right? And if you want to make a preliminary truth table where instead of 0, 1 you say closed open, and instead of 0, 1 you say off on, right? That can help explain what you actually observed, and then you translate it into the truth table. And these truth tables should always be 0, 1, right? Instead of on, off, true, false, open, closed, yes, no, things like that. Standard truth table just uses 0, 1s. All right, so this is a weird kind of inverter, right? Using 2 inverters and some LEDs, but basically the lights do the opposite of whatever the switch's logic level is. Okay, experiments 3, 4, and 5. Here you were not given a schematic, you were given kind of like a picture from Tinkercad, right? You don't want to draw your own schematics with these chips in here, right? Because somebody looking at this doesn't know what this function is, how are A and B being turned into an output, until they look at this, see this, look up the data sheet for that, see what pins 1, 2, and 3 are, right? So if you were drawing this circuit from scratch, you would use a symbol for an AND gate, and A and B would go in and the output would go through an LED. Now, you're welcome to just include this in your lab report because this is what you were given, and your goal was not to, you know, build a logic diagram from this. It was just to implement this in Tinkercad and see what it does. But your truth table should respect this figure. So what are the inputs called? A and B. So your truth table should look something like this. A and B, those are my inputs. And your output is just called output, so call it output. and we're making a truth table, so you're going through all the combinations of your input. And so what does it mean to say that the input A is a 0? Well, it means that this switch is closed, because when the switch is closed, this point gets pulled down to ground. That's a logic 0. So to test what happens when the inputs are 0, 0, you want to close both of these switches. Which means if your switch looks like this, you want them in this position, not the position that's, you want them in the position that says on, right? Because that means close this top part with the bottom. So when the switch is in the on position, the switch is closed. So you got to tie all these things together, and it's little minutia details, right? But they totally change the meaning of this thing, right? And ultimately, you know, you have a circuit that's you know, controlling some huge piece of equipment. Ultimately, there's a 1 or a 0 somewhere which says go or no go, right? And those make a huge difference. So part of the practice of these labs is, you know, getting down to that level of detail and tying it all together. All right, so if the switches are closed, that's a 0, 0. And this should be an AND gate, so 0, 0 should output a 0. And in fact, all of these should output a 0, except for the last one, which outputs a 1. And we're almost always going to say an output of 1 LED is on, right? Logic value of 1 means 5 volts, and the other end of the LED is connected to ground. So when your LED is lit, that means you're getting a logic 1 out. So your LED should be off in all cases except when both of these switches are closed or in the on position. Sorry, off. Yeah, it's confusing, right? LED should be off in all cases except when both of these inputs are logic 1, which means that they're in the open position, okay, the off position. So when they're down like this, the LED should be on. All right, experiment 4, same thing, but you're using an OR gate. You're going in pins 5 and 6, out pins 4 and 5, out 6. Build the circuit, make a truth table. And then experiment 5, this was the funny one, right? You're using an inverter. You have 2 inputs, A and B, and 1 output. But here, the input A is really, it's a red herring. It's not being used. It's just there to distract. So your output only depends on B. So your truth table for that would look something like this. Right, where the output is simply the complement of the input. And if you make a K-map from this and you simplify, you'll find the following equation. Output is just equal to B bar. And that's exactly the circuit that you've got here. Your output comes from pin 4, that's just the output of the inverter, fed from pin 3, which is coming from input B. So output equals the complement of B. All right, one other general comment on those first few experiments on labs in general, okay? You are absolutely welcome / encouraged to take this picture from the lab and put that into your lab report, okay? As long as it doesn't say draw your own circuit or something like that, you can take a picture of the circuit that you've been given and put that in your lab report, but reference it, okay? Put a note down here, right below the figure, and say, figure taken from, you know, Digital Logic Design Online version 1, or something like that, right? Find some way to reference it, so that people don't think you're claiming this is your picture, okay? This is a standard thing in publishing. You use material from other sources, but you always have to cite where that material came from, because if you don't cite it, the assumption is it's yours. And if you take words verbatim from the lab, for example, if you say, you know, a typical dual inline 4-switch package contains 4 independent switches, right? You got to cite that. Okay, the rule of thumb is, I think, 5 words in a row is the most that you can do without citing. Okay, so you can use material from the labs themselves, just put a note on there saying that it came from the lab or the website or wherever. All right, so let's talk about the traffic control signal, experiment 6. So where do I start? All right, let's talk about what we needed to do in here, okay? First of all, you wanted to draw a picture of the intersection, okay, which most people did. I do want your intersection to look the way that we've been discussing it in class, which is it runs from west to east, and the third lane is on the south. And I want you to label these west, south, east. When you're labeling the sensors, when you're labeling the lights, I want you to use W, S, and E to indicate which ones are which. Don't use A, B, C, 1, 2, 3, X, Y, Z. Okay, so I've mentioned this every time that we've talked about this, and I mentioned this in comments on Lab 1, and I didn't take off points. So I'm taking off points on Lab 2. I'll take off points for the rest of the labs. So stick to WSE, okay? So draw your intersection and define the inputs and output variables. So something like this, right? So WSE are car sensors, and then have a pair of lights, green west, red west, green south, red south, green east, red east. And you can say green west, red west, green south, red south, green east, red east are lights. And you can note, car on right has priority. Right? This is the problem definition. This is what do you want to do? I want to make a traffic light controller for this intersection, right? With 3 sensors and 6 lights, and the rule that the car on the right has priority. Okay? System diagram. Show the inputs and the outputs. Put arrows on these so you know what's an input and what's an output, because some places putting something on the left might mean that it's an output. Or you might have things on the bottom or the top. Or you might have inputs and outputs on the same side. So make an arrow so it's clear what's an input, what's an output. And then label these. And the order doesn't really matter. And then indicate what a 1 and a 0 means. So 0, car, not present. 1, car present. 0 off, 1 on. Alright, so that's a complete system diagram. Okay? This part right here. This is the problem definition, this is the system diagram. Alright, let me describe the general steps here, and we'll go through this. We have a problem definition. That's going to take us to a system diagram. That's what we've got here. That's going to take us to a truth table. So based on what we want this system to do, we can write a truth table to describe that behavior, in a very systematic way. So what's our truth table look like for this? Well, we know we have 3 inputs, west, south, and east. And we have 6 outputs. And we know that the car on the right should always have priority, which means any time that there's a car to the east, that's the one that's going to have the green light. So green east is going to be 1 any time that our east car sensor is a 1. And if there's not a car to the east, but there's a car somewhere else, then we're not going to give east a green light. We're going to let somebody else go. And you can choose what you want to do in the case where there's no cars present. So that could be a don't care, but we don't want all the lights to be green, right? So pick some values. Okay, if there's if there's a car on the east, nobody else is going to have a green light. But if the east is clear, then south gets priority. So here there's a car to the south, south is going to get green, and west is going to have to wait. And here there's a car to the south, so south will get a light, and west is going to have to wait. And this fifth row down here, there's no car on the east or the south, there's just a car on the west, so that's the case where west gets to go. So west will be allowed to go there, the other lights will be off. And what do you want to do in this case? Well, it's totally up to you. But it's going to make your design easier to build, actually, if you just went ahead and did this. But you can do whatever you want. Okay, so I'll put that in parentheses. Alright, and then the west is just the opposite of, the reds are just the opposites of the greens. So this will be 0, 1, 1. This will be 1, 1, 0, 1, 0, 1, 1, 1, 0. Because we know that the red light is always doing whatever the opposite of the green light's behavior is. So there's our truth table. Okay, and that's derived from the problem definition. Alright, once you have a truth table, you go to equations. So you can write a sum of products, you can write a product of sums, you can do whatever you want, but you're turning your truth table into equations because it's almost impossible for most humans to go from this to a circuit diagram, right? We need to have equations because when we have equations, that's in the language of and, or, not, and we have physical components, gates, that correspond to those. So before you build your circuit, you need to turn your truth table into equations. And once you have equations, you want to simplify them. Why? Because simpler equations mean simpler circuits. And then you don't start building, then you make a circuit diagram. Which is something with AND gates and OR gates and NOTs and things like that. But it may not have switches and LEDs, right? But it's capturing the logic of it. So this is sometimes called a logic diagram. And once you have a logic diagram, you're still not ready to build the circuit. We want to turn this into a wiring diagram. And this is where we put down pin numbers and we identify which physical chip we're going to use for each gate or set of gates. And we put in switches with resistors and LEDs and connection to power and ground and all of those details. And we end up with this roadmap that we can hand to somebody who knows nothing about this problem, and they can build the circuit. Okay, it's got enough detail that all you have to do is pull the right pieces out of your parts box, put them in the board according to this diagram, and you're done with your circuit. Once you have that diagram, then you can actually build the physical circuit, which for us is Tinkercad, right? Okay, here's the thing on Lab 2. Almost everybody went from here all the way over to here. And I didn't get to see any of this stuff. And this is the good stuff, right? This is the hard work that you've been doing. This is the K-maps. This is the truth tables. This is the sum of products. It's all that stuff. It's looking up the parts and saying, which pin do I connect to, right? That's what all of this stuff is. Go ahead and put that in your lab report, okay? Make sure you share that process with the reader, because the idea of a technical publication is other people will try to reproduce your work, okay? This is how science works. Somebody has a theory, they come up with an experiment to try to support or refute that theory, they perform the experiment, and then they document it. They write a paper that says, you know, here's what we're trying to prove. Here's the experiment we came up with. This was the procedure. Here's the steps that we followed. Here's the observations we made. Here's the conclusion. You know, gravity exists. The Earth is flat, whatever, okay? And then they publish this, and other people say, this is a proof that the Earth is flat. I want to check this myself. And they'll follow your steps that you've outlined in your report and try to come to the same conclusion. And if they're following it and they do one of the experiments and they come up with a different observation, they can publish that and say, you know, when I tried this, I observed something different. And the scientific community can look at that and do their own versions of the experiments and so on and so forth. This is science, right? This is how it works. This is what Copernicus did for us, right? He sort of pioneered the scientific method, hypothesis, experimentation, analysis. So all of this is critical to getting to the physical circuit and observing that when you flip these two switches to the off position, the LED turns on, right? So put all that stuff in there. That's all really good stuff, and it's the hardest part of it, right? In some sense. So get credit for that. All right. So this is the truth table you should be working with for the intersection, assuming that you're using 0, 1 for no car, and 0, 1 for off and on for your lights, which everybody is. You could have designed this and said, you know, my car's sensor is going to do a 1 when there's no car and a 0 when there is a car. That's perfectly valid. You'll get a different truth table, different equations, different circuit. But in the end, the behavior of the intersection control will be the same. Okay? Which is you'll have 3 lanes, and the car that has highest priority will have a green light, and other cars will have red lights. All right, where are we? We are at 12:38. Let me go through a start to finish example of this process up to. I'm not going to do the physical circuit, but I want to go through the full set of steps for this for a different problem, fictitious problem. So let's design. Design a control system for a kitchen. And this is an industrial kitchen, so it needs a fancy control system. And we're basically going to control an oven. So we've got an oven for baking things, and we have an exhaust fan. Right, which vents exhaust out from our baking endeavors, and we want a control system for this. So we're going to have 3 switches. Okay, we're going to have a switch labeled bake, which should turn on the oven. So when you want to bake something, you use the bake switch, okay? And we should have a fan button which says turn on the fan motor. And we're going to have a shutdown button, which is an emergency shutdown, in case your cake is burning or something, right? So 3 inputs. And the outputs are going to be basically a heating element, a motor, and an alert light, an alarm light. Okay, so the bake switch just turns on the oven. The fan switch will turn on the fan motor, but only if you're baking something. If the oven is off and you try to turn on the fan, it's not going to do anything. Okay, because there's no need to run the fan. And the shutdown is an emergency shutdown which says, if baking, turn off the oven and turn off the fan. And light an alert indicator. Alright, so this is a kind of weird high pressure kitchen to work in. Hit the bake switch to turn the oven on. Hit the fan switch if you want to turn on the exhaust fan. And if you need to stop everything quickly, hit the shutdown button, right? And if the oven is baking, it will turn the oven off. If the fan is on, it will turn the fan off, and it will turn on an alert indicator. If you're not baking, if the oven is off and you hit the shutdown, it doesn't do anything, right? Somebody just bumped into it probably, so we don't turn on the alert indicator, and the oven and the fan stay off. Okay, this is a problem definition. This is what your customer comes to you with and hands this to you and explains it to you and says, can you build me a system for this? And you say, yes, I can. Okay, so you take this and you want to turn it into a circuit. Okay, that's the problem definition. What's our next step? System diagram. Let's identify the inputs and the outputs. So this is problem definition. Let me make sure I'm recording this. I am recording it, good. Okay, so that's the problem definition. Let's do the system diagram. Alright, we have three inputs, bake, fan, and shutdown. I'm going to call these B, F, and S. So B is for bake, F is for fan, S is for shutdown. And we have three outputs, which I will call heater, motor, and alert. Oh, okay. Well, sorry to whoever missed 40 minutes of the class, but it's being recorded, so you're good. All right, so here's our system diagram, right? We don't know what B is and F and S and this kind of stuff. We've got to define what these things mean, okay? So B, bake control. 1 equals bake. 0 equals off. Okay, that's pretty much what we would have guessed, but you know, spell it out. F is the fan control. 1 equals fan on. 0 equals fan off. Okay, S is the shutdown. Well, you know, I'm going to do something different here. I'm going to think about potential failure of the control system, right? So if I want my, if I decide my shutdown is going to be a 1 when I want to shut things down, what happens if the battery controlling my circuitry has died? And I try to put a logic 1 in by flipping the switch, and I can't because there's no current anywhere, right? A more fail-safe mode might be 0 equals shutdown, 1 equals normal operation. So I gotta have current going into my system in order to generate this signal 1 which says everything's okay, keep baking. Okay? But in reality, the only reason I'm doing this is just to show you why it's important to specify what a 0 and a 1 mean. Right? Because we don't have an inherent sense of what should a shutdown signal look like. Right? Should it be a 1 or a 0 to shut down? Other than the fact that I called it shutdown, right? But if I called it run, maybe a 1 means run, 0 means don't run. So spec these out, right? Specify them exactly. And then on the output side, heater, let's say 1 equals on, 0 equals off. But again, you know, depending on where you buy this heater from, it might say put a logic 0 into the heating unit to turn it on. There's systems that work like that. Okay, motor, 1 equals on, 0 equals off. And our alert, that's just going to be a plain old LED, so we'll do 1 equals on, 0 equals off. Okay, there's a whole system diagram. So now we know what the inputs are, what the outputs are, and what the ones and zeros mean. We're ready to turn that into a truth table. And once we have a truth table, these 2 pages, we can forget about them. Once we have a truth table, it's an engineering 250 problem. You could hand it to a 250 student and say, build me a circuit, and they wouldn't have to know that they were building a control system for a kitchen. They would just be doing an engineering 250 exercise. So the truth table is where we make the transition from, you know, all of the kind of multi-formed, sloppy, potential error-prone description of a problem to a very precise, well-defined statement of what we're trying to do. So we use our system diagram to start our truth table. We have 3 inputs, B, F, and S. So B, F, S. And with 3 inputs, we have 8 combinations. And we have 3 outputs, heater, motor, alert. Alright, here's an important thing to keep in mind. Whatever you put in this table, that's what you're going to build. So you really want what you put in this table to be correct. If you misinterpret the problem definition and you fill in a table that's different from what you want, you're going to build a circuit that implements the wrong behavior. And you're going to end up going back to the drawing board, literally, right? You're going to have to go back to the original problem definition and redo the ones and zeros here and then go from there. Because, you know, most of our hard work is from the truth table on out. So be really careful when you fill this out. And when you're done, right, typically you would get an approval from somebody, a second set of eyes, to look at the problem definition truth table and sign off and say approved, right? And now you got 2 people whose career is on the line if something goes wrong. So it's just more levels of check. All right, so what do we want? We want the bake. Let's look at the shutdown first, because the shutdown is a huge override, right? Anytime the shutdown is on, we want the baking to be off and the fan to be off. So let's look at the shutdown equals 1 cases. Turn the heater and the motor off. All right, and the alert should turn on whenever you shut down if you were baking. Okay, so look at the cases where we're asking for a shutdown and we were also baking. That's right here. We were saying let's bake, and then we hit the shutdown, so the alert should go on. And here we were saying let's bake and let's have the fan on, and let's shut down, so that'll be an alert. But in these cases, you know, there's no shutdown requested, so we don't have an alert. And in this case, we hit the shutdown button, but nothing was baking, the fan wasn't on, so no alert light is necessary. Here we weren't baking, so no alert light is necessary. So there's the alert indicator, right? Let's talk about the heater for the oven. So if you're not asking for baking, heater's going to be off. If you're asking for baking, the heater's going to be on, except, you know, when we've got the shutdown signal. So here we're baking, no shutdown, so the heater's on. Here we're baking, no shutdown, so the heater is on. Okay, last one is the fan motor. So if the fan switch is 0, we definitely don't need the fan motor on. In this third row, you've turned on the fan switch, but we're not baking. So remember, the description says fan, turn on the fan motor only if baking. So if we're not baking and the fan switch is on, we still keep the fan motor off. It only gets turned on in 1 case, which is when we're trying to bake and we've turned on the fan switch. That should be a 1. So there's our truth table. Okay. And you've got your system design and so on, but you've turned it into a truth table, right? You can rip that up and tear it into little pieces because you never need to look at it again, right? No, don't do that. So keep your problem definition, right, and your system diagram, but now we're just going to work with the truth table, okay? We want to turn this into a circuit. So we've done this, we've done this, we've done this. All right, next step, come up with equations. This is sum of products, product of sums, K-maps, etc. So you could write this as, you know, a sum of products. There's only a single term here. There's only two one terms in these. I'm going to go straight to a K-map. Okay, so I'm going to do these in one step because that's what K-maps do for us. So let's make a K-map, and we're going to have to do this once for each output. So we have three input variables, B, F, and S. So I'm going to label my K-map like this. And let's do the heater first. So the heater, I have a 1 down here where B and F are 1, 0, and S is a 0. So I want a 1 right there. And I have a 1 where B and F are both 1s and S is 0. So I have a 1 right there. And those are the only ones I have, so I can cover that with a rectangle like this. And if I look at the equation for that, B has to be a 1, F doesn't matter, S has to be a 0. So the heater corresponds to the equation just B, S bar. So let me write my equations next to this. And these are equations simplified. So heater equals B S bar. All right. So if you were doing a lab report, right, you would include this in your lab report to say, you know, simplification of equation for heater, and there's the K-map, there's the rectangles, and so on. Take a picture of it, erase it, go on to the next one, right? This is a nice thing about electronic reports. So let's look at the motor. So the motor has just a single one. Well, I could put it in the K-map, but it's not going to simplify. I'm just going to get the plain old sum of products. So what's the motor look like? B, F, S bar. All right, so that's the motor. Yes, problem definition is definitely really helpful because it drives this, right? All right, so there's the motor. Last system is the alert. So the alert has two 1 values. So the first is for B equals 1, F is 0. So B is 1, F is 0. That's this bottom row. And S is equal to 1, so we have a 1 right there. And then the 7th row is 1, 1, 1, 1, 1, 1, that's right here. So we cover this with a single 2 by 1 rectangle. And we write the equation from the K-map, and it looks like B has to be 1, F does not matter, and S has to be 1. And so our alert is B ANDed with S. And there's your equations. So this is simplification of equations. With K-maps. And there's the simplified equations. All right, now we're ready to make a logic diagram. So we have three inputs, B, F, and S. And we can do it like this, right? This way that we talked about week 1, where you run your inputs vertically. You provide true and complemented versions of them. And then we just make some logic gates. Well, the heater should become an AND of B with S bar. So we'll make an AND gate. We'll take one input from B. We'll take one input from S bar. I went too far with my wire, right? And the output, I'll label that B S bar. That's the heater. And then the motor is B ANDed with F ANDed with S bar. So that's a bigger AND gate. And it's B ANDed with F ANDed with S bar. And that's the motor. And then the alert is just B ANDed with S. So run a wire from B, run a wire from S. That's B ANDed with S. That's the alert. Okay, so let's call this a logic diagram. It's still not a complete wiring diagram. If someone handed you this and asked you to build the circuit in Tinkercad, you would have to do a lot of online work. You would have to figure out, which gates correspond to these. You'd have to look up their pin numbers. You'd have to decide which pins to use for each of these. You'd have to wire up switches and so on. So this is a logic diagram, right? It's written in this universal language of logic symbols, inverters, AND gates, and so on. But it's not quite a wiring diagram. Okay, so we did equations. So this is a logic diagram, circuit diagram. But we want to do one more step before we actually build. We want to turn this into a wiring diagram. Okay, so let's make this wiring diagram. Okay, well, we don't need this inverted F line. We don't need the inverted B line. And we're doing B ANDed with S bar ANDed with F. We've already got B ANDed with S bar up here. We could just AND this with F, right? So you play around with this and you try to turn it into something that's going to be as painless as possible to actually build. So this is, part of the art of circuit design. And get yourself a good sharp pencil and a nice eraser and mess around with it, right? So I'm thinking I'm going to take B and I'm going to take S, and I'm definitely going to AND those together. And that's going to go to my heater. And since I also want B ANDed with S bar ANDed with F, I'm just going to take F and I'm going to AND it with this. And that's going to be my motor. I forgot to invert S. So take S and run it through an inverter. So now I have S bar ANDed with B, so that's B S bar. And then this is B S bar F. That's our motor. And then our alert is B ANDed with S. So let's take these and just AND those together. And there's our alert. Alright, so that's a simpler logic diagram. We've gotten rid of the extraneous inverters that we had here, for example, and we've combined some logic here. Now you don't have to do this, right? But if you're actually building this, here I had 3 gates to wire together. One of them was a 3 input. Here I've got 3 gates, but they're all 2 input devices, right? Which, guess what? I can get that from a single chip. Okay, so let's turn this into an actual wiring diagram. So I need switches. So our outputs, we're just going to turn those into LEDs, okay, because we're just going to test this circuit. So we need switches for these. So how do we make a switch? 5 volts goes through a resistor. And you want to label this as a 1K resistor so the person building the circuit knows to get a 1K resistor out of the box. Hook it up to 5 volts. And then put a switch in here that connects to ground. And I'm going to label this B. Alright. And then I'm going to make another switch. 5 volts. And I'm going to label this S. So that's going to be that input. And I'll make a third switch. Goes to ground. I'm going to label that F. That's the fan switch. Alright, and then B and S are going to get ANDed to generate the alert signals. So remember, your signals come off of here. So there's B and S. And I want those to go into an AND gate. And I want that to generate an alert signal. So that's going to go through an LED. And a 1K resistor and over to ground. And I'm going to call this alert. Alright, my heater signal is going to be an AND of B and S bar. So S is going to have to go through an inverter. And then B is going to get ANDed with that. So make it clear when something is connected or not connected. So there's an AND gate. And this will go to an LED for our output. And this is the heater. And then finally the motor is the AND of the heater output, right? This line right here, and the fan input. So let's take this and pull off a copy of B ANDed with S bar. Go through a 1K resistor to ground, and that's our motor. All right, so this is still a logic diagram. But it's got more information to it. It's got the switches, it's got the LEDs, and it's ready to be turned into a wiring diagram. So how do we make a wiring diagram? Well, put something up here, component ID block. Okay, typically goes in the upper right, and it's going to have an identification, and we're going to identify each of these logic gates using a symbol like U1 or U2. We're going to say what the part number is, 74HC04, etc. We're going to say where we connect to power, where we connect to ground, and it's nice to say where do we not connect to anything. Alright, so now you go to the web. You can go to engrcs.com or linux.engrcs.com. This is the slightly newer version. And I'm going to go to resources, component specifications, and I know I want some inverter, so I'm going to pull up a 7404 hex inverter. And we've looked at this particular data sheet before, so we saw that there were 6 inverters. We can come in on pin 1, out pin 2. So this is what we're going to use for our inverter. So I'm going to label my inverter U1. And up here I'm going to say U1 is a 74 HC04 if we're doing Tinkercad. and I know VCC goes on pin 14 and ground goes on pin 7, I can use any of the inverters that I want from here. I have 6 of them available. So easiest one usually just come in on pin 1, out on pin 2, right? That's one of our 6 inverters, in 1A, out 1Y. So we can go in 1 and come out 2, or we could go in pin 13 and come out pin 12, right? Does not matter, but you have to make a choice. And then you want to put it on your wiring diagram. Okay, so I'll go in 1, come out 2. So I'm going to just label this input with a 1 and label the output with a 2. Alright, I also have 3 AND gates. Let's go back to our component specifications. Look for an AND gate, 74 LSO8, 2 input AND. And here we've got a kind of nicer picture. So there's 4 AND gates inside here. We only need 3, so we only need 1 chip, right? This is helpful. So I'm going to use 1 chip, 74 HC08. So I'm going to make a new entry in my component ID block, U2. This is going to be a 74 HC08, VCC on 14, ground on 7. And each of these I'm going to take from this chip, which I'm calling U2. And I gotta choose which pins to use. Well, I have 1 AND gate. I can come in pins 1, 2, and out 3. So I'll just use that one here. I'll come in pin 1, 2, and out 3. Another AND gate, I can come in 4 and 5 and out 6. So I'll label this 4, 5 for the input, 6 for the output. I have a third one, I can come in 10 and 9 and come out 8. So I'll pick that one, come in 10 and 9 and go out 8. And now everything is labeled. Okay, so let's fill in which pins don't have connections up here. On my AND gate, I did not use 13, 12, or 11, but I used every other pin. So no connection here is 11 through 13. On my hex inverter, other than power and ground, I only used pins 1 and 2. So 3 through 6 was unused. And I used pins 14 for power, but I did not use 8 through 13. So 8 through 13 are also unused. Alright, there's a wiring diagram. And down here, you know, you can put a box that says, you know, kitchen, control system, and this is version 1.0, designer, and you can put your name in there and date, and you can put the date, and if you're doing this, you know, in a job setting, you would get an approval from somebody. And you take it to your boss or your coworker or someone, and they look at this and they say, yes, we want to build 1 million of these, and they put their signature there, right? And it's you know, helping to guarantee that when you take this and you send it to the manufacturing department, they're not building 1 million pieces of junk, right? They're building 1 million pieces of a circuit that has been, you know, designed by someone and approved by someone and maybe approved by 2 people and so on, okay? And this is, you know, the last step before the physical circuit. Okay, you would like to do all of that before you sit down to Tinkercad or before you go into the Collaboratorium and start pulling out a protoboard and parts. Okay, because once you have this, you can effectively forget about all of this. Okay, all those details, they're contained in here. And when you're trying to debug your circuit, if it's not working correctly, you don't want to be going back to the problem definition or the K-maps or things like that. You just want to be looking at this. And to debug your circuit is really, there's an algorithm you can use, right? For example, suppose you turn on the bake switch and you turn off the shutdown, right? And you turn on the fan, and for some reason your alert signal is coming on. Okay? Well, if you feel like this alert should be off, what do? Take a voltage reading right here, pin 3, chip U2. And make sure that you're getting a 0 out of there. If you're not getting a 0, right, there's a problem. If you're expecting a 0 out of here, but you're getting a 1, it means that both of these are 1s, and you expected one of them to be a 0. So if you expected this to be a 0, take a voltage reading there. If you're getting a logic 1, there's a problem with your switch. If you expected pin 2 to be 0 and it's 5 volts instead, there's a problem right here. There's a problem with that switch. Right? If you expect pin 6 to be a 1 and it's a 0, right, then one of these is accidentally a 0. So check that. If that's a 1, check this. If it's a 0, there's a problem back here. If this is a 1 and this is a 1 and this is a 0, there's probably a problem with your chip. Right? So you can isolate your problem. You can trace it back. Right? If this is supposed to be a 0, but it's actually a 1, check pin 2 of this. If that's a 0 and that's a 1, you've got a wiring problem. Check your wire between pin 2 on U1 and pin 5 on U2. Maybe it's in the wrong hole. Maybe it's a bad wire. Maybe you forgot to put that wire in at all. Right? But if this is supposed to be a 1 and it's a 0 and this is also a 0, right, well, there's a problem with the input. The input should have been a 0, so the output was a 1. So check this. And if this is not what you're expecting, trace it back. If this is what you're expecting and the output's not what you're expecting, the problem's with the inverter. So if you build your circuit and it's not working correctly, you can start from the point where you know there's something wrong and work backwards, as long as you have a wiring diagram. Now, if you don't have a wiring diagram, you want this LED to be on, but it's not on, you got to physically follow the wire on the proto board, see what it's connected to. Well, it's on pin 3 of this chip. What is that? Well, you got to pull out the data sheet and see what that pin is supposed to be, and then see where these are supposed to come from, and it becomes just a much more, this is where people usually just rip all the wires out and start over, right? So this lets you actually debug. So this is the wiring diagram that you're ultimately after for experiment 3, for lab 3, okay? So we're going to take a short break, and then I'm going to talk you through the details of lab 3, and I posted some specific guidelines to help you get 100% on lab 3. So let's take a 5-minute break. We'll come back. We'll go through those guidelines, and then we'll start talking about some new material. All right, so I'll see you back in a few minutes. All right, so let's continue. So hopefully that example made some sense and helps with what we mean by a wiring diagram. And also what we mean by just a plain old logic diagram, okay? So you're going to do both of these for lab 3. So with lab 3, I posted some hopefully clarifying details. So let's take a look at that. So lab 3 has a single experiment, which is, continuing with the intersection control signal system. So, 3-way intersection, same as usual. Complete the following steps. Sketch the intersection with variables identified and respective values defined. Okay, that's the problem definition. System diagram, it doesn't say it in here, but it says it in the other notes. Truth table, okay. And then you're going to make a sum of products set of equations and draw a logic diagram, okay, something like this, from the sum of product equations without simplifying them, okay? And then you're going to write a product of sums set of expressions, and you're going to make a logic diagram from those without simplifying, okay? These steps, 3 and 4, take a lot of work, okay? My suggestion, start on this as soon as you can. Give yourself some time, right? Maybe do the first few steps, take a break. Come back, do step 3. That's going to take, maybe an hour to do. And then take a break. Come back another day or later that day or something, and then do the product of sums. That's going to take a long time too. It's a lot of writing, it's a lot of drawing, okay? I really don't recommend doing this with a schematic tool. I recommend doing this on paper, okay? And these are primarily for you because you want to see, if I don't simplify and I do sum of products, what does my circuit look like? If I don't simplify and I do product of sums, what does my circuit look like? And then in step 5, you're going to do an analysis. And this can be whatever you want it to be, okay? But compare these two outputs and decide which one would you rather build. Okay, it's totally subjective. It's up to you. Personal preference, you know, what you have experience with and so on. But do an analysis and describe it. Why do you think you want to build a sum of products one or the product of sum one? And then you're going to minimize your equations using K-maps, and you're going to work your way to a full wiring diagram for your traffic control system. Okay? And then you're going to implement that and you're going to test it. So here's what I posted on Canvas. So to receive full credit, you need to do the following. First of all, explain what you're doing. Don't just jump in and start you know, writing equations and truth tables. Put in a sentence saying, you know, what are we doing in this lab? That's the introduction, okay? Include a system diagram, all of the inputs and outputs. Use arrows to show which are inputs and outputs. Label all of those arrows and then say what a 0 or 1 means, okay? Use west, south, east for the 3 sides of the intersection. Draw a picture of the intersection. Be consistent, okay? Use the same labels that you used in your system diagram. Write a truth table with 3 inputs, 6 outputs using the same labels from the system diagram. Okay, make sure you include all the rows and columns. Some people forgot a row here or a column there. Okay, make sure it's got, you know, 3 inputs, which means 8 rows, 6 outputs. So you should have a total of 24 ones and zeros on the left and a total of 48 on the right. Right, 6 times 8. And then unminimize sum of product equations from your truth table. And sketch a circuit from those using logic symbols, not pictures of chips, right? And you do not need to include inputs and outputs here, okay? You don't need to put in the switches and the LEDs. And then do an unminimized product of sum equations and sketch a circuit from those using logic symbols, okay? So like this, right? And label your inputs and outputs, but you don't need to put switches and LEDs in, okay? That's not going to affect your analysis. You're looking for the complexity of the logic piece of this. Okay, so, oh boy, that's weird. I think I just took a picture of my video. It's still going. Okay, so unminimized product of sums equations, right? And it's going to be 6 equations because you have 6 outputs, and then sketch your circuit. Okay, and remember when you have, you know, multiple outputs, you're going to have multiple equations, but you want to build one circuit diagram that, you know, produces all of your outputs from the set of inputs, as opposed to one circuit for alert, one for heater, one for motor. You can do that as you know, a step along the way, but you want a single circuit that generates all the outputs. Okay, so unminimized sum of products, unminimized product of sums, and then compare the above 2 sets of equations and designs and decide which one to use. Explain your thinking and why you chose one over the other. Okay, that's an important step. That's part of your job as an engineer, is to like do this kind of analysis and say we should do a sum of products. Here's why, right? And I'm not really, you know, looking for a particular right answer here. It's up to you. Do the best job you can. If it makes no difference to you which one you do, right, go ahead and say that and then do one, but chances are one's going to look different from the other. Okay, once you've decided, okay, I'm going to do an SOP or I'm going to do a POS, minimize the equations using K-maps and make sure you show those K-maps. Okay, you're probably going to have at least 3 K-maps. But, you know, at this point, many of you have observed that when you're making a traffic light control system, you have all this logic that generates green west. You can just run this through an inverter to generate red west. Okay, Well, that's fine. Just go ahead and mention that, which most of you already did, right, if you were doing this. But, you know, this is not what's going to come out of your sum of products, okay? But, you know, you can make this observation as a clever engineer and say, you know, red west is just the complement of green west. So I'm just going to use the equation red west equals green west bar, right? And so you only really need to minimize 3 equations, right, for your west, east, and south green lights, and then make the reds the complement. Or if you do a product of sums, maybe you'll write equations for the red lights and then make the greens the complements of those. It's totally up to you, okay? This is a very creative, very designy part of the process, okay? Once you have those equations, now make your full wiring diagram, which is the thing we went through at the end before our break. So a component ID block in the upper right corner. List the components, show power, ground, connections, and pin numbers. Power and ground connection pin numbers. Logic symbols, right? So, you know, those symbols for AND gates, OR gates, inverters, that kind of stuff. With a part ID, U1, U2, etc. from the component ID block. Pin numbers on each of the inputs and outputs for each gate. All the switches, LEDs, and resistors, and everything labeled. Okay, all of the inputs labeled, all the outputs labeled, and those should match what's in your system diagram, in your truth table, in your 3 sets of equations, right? Everything should be consistent. And make sure there's a cover sheet, 1-sentence introduction, and then conclusions, lessons learned, and a new experiment at the end. And you're good. That's 100%. Okay? I want everybody to get 100% on this. So make sure you got all these steps, okay? It's only one experiment, right? Only in quotation marks, but it's a big experiment, okay? So plan on spending a lot of time on this. And if you can work calmly, you'll be more successful in the end, right? If you're not trying to get this done in a hurry, if you're letting yourself work across multiple sheets of paper, right, and then you're putting those together into a single PDF so it forms a nice consistent story step to step to step, right, you're going to be more successful. The difference between SOP and POS is really just, you know, once you have your truth table, how do you write an equation corresponding to that? So we did a product of sums. If I were to do, we did a sum of products. If I was to write a POS, right, heater equals B or F or S, ANDed with B or F or S bar, ANDed with B or F bar or S, ANDed with B or F bar or S bar, ANDed with B bar or F, nope, that one's a 1, ANDed with B bar or F or S bar, ANDed with our last 0, which is B bar or F bar or S bar. So that's the product of sums equation I get for a heater. This is the sum of products equation I get for a heater. Fundamentally different, okay? And so for your traffic lights, right, the equation for your green light and the equation for your green light in an SOP or POS will look fundamentally different. And this will not simply be the equation for the red light. Okay, this is not the complement of that. It's a product of sums. Sum. Take the product of them. Is it okay that we reuse the SOP equation for the traffic light from lab 2? As long as it's unsimplified, yes. And as long as you have 6 equations, right, 1 for each light. And you cannot do you know, this trick of setting red west equal to the complement of green west. That's a simplification. I want you to go straight from the truth table, write a sum of products for each of your 6 outputs, or a product of sums for each of your 6 outputs. Okay? It is a lot of work. It's about the most work that you can get on this particular circuit. Okay? But I really want you to do the unsimplified POS and then SOP and compare them. Okay? So think of it as a humongous homework problem that you get lab credit for. All right, any other questions? All right, cool. That was the stuff I wanted to go over related to what we've already done and related to Lab 3. Let me take a quick look through Homework 3 with you. And make some comments on that. So, there's a few problems in here that I said you could skip. So question 1 you can definitely do. Okay, determine the number of unique functions possible for n independent variables. So think about this. Think about a truth table of 3 variables, right? How many different truth tables are there, right? Number of unique functions is basically how many unique truth tables are there, because each truth table gives you a function. So think about this and ask questions about it next time or in office hours. But it's a good thought exercise. Okay, and don't just take the solve problem and plug in a 6 or a 7 for n, because then you miss the benefit of like the thought exercise part. Okay, question 2, analyze a logic circuit in order to come up with a logic function that's an equation, and then minimize it. Okay, this is a circuit with a lot of gates in it. So turn this into an equation. F is some function of a0 through a3. Minimize it, right? Probably make a truth table, put it into a K-map, cover rectangles, write the sum of products you get, and then write down that minimized logic function. So it's an analysis question. Okay, question 3, we talked before about the universality of NOR gates, the fact that you can use a NOR gate to implement a NOT, which means you can implement an OR, and if you can do an OR and a NOT, you can do a NAND by De Morgan's theorem, and if you can do a NAND and a NOT, you can do an AND. So you can implement all of these gates using NOR gates. Okay, notation, this little bubble here means this AND gate is taking in C and the complement of D, and then it's complementing the output. So this is a NAND gate, but D is basically going through an inverter before it gets to that NAND gate. This is notation you'll see in a lot of schematics you encounter. They're called bubbles. Bubbles basically mean invert. And we invert so many times that we just draw a bubble sometimes instead of an inverter. That's exactly what we do with a NAND gate. This is really an AND gate with the output going through an inverter, but the little bubble here says take the AND gate's output, flip it. Okay, well we can flip inputs too. So this says take D, put it through an inverter, and put that inverted input into this gate. Well, so we just draw a bubble there, and it means just flip D. Alright, obtain a minimum SOP using compressed K-maps. So we're not going to compress K-maps, so skip question 4. Question 5 is another form of compression, so I believe I said to skip this one also. And then question 6 is another form of compressing a K-map, so we're skipping question 6. So 4, 5, 6 don't do. Question 7 deals with demultiplexers, which we're going to talk about briefly, in a brief moment from now. So, but you'll have this circuit. It has 3 inputs and 3 outputs, F0, 1, 2, and you're trying to write these in compact minterm form. Okay, so we have to talk about what this demultiplexer does, but we'll do that shortly. And then question 8 uses a multiplexer, same thing. We have 2 inputs A, B, and we have an input here C, and we want to write an output F. 2 inputs A, B, 2 other inputs A0, A1, and we want to write F in terms of A0, A1, A, and B. Okay, so we want to write F like this in compact minterm form. So we have to talk about what a mux does. Okay, but that's our next subject, is muxers and demuxers. And then question 9 is looking at 3 functions, F1, 2, and 3, each written as a sum of products. You want to write product of sums for these, but you want to try to reuse terms. Okay, so for example, if we're generating F1 equals AB or B bar D or CD, and F2 equals AB bar or C bar D bar or B bar D or AD, right? You want to observe that this term can be reused in both of these expressions. So when you come up, sorry, you couldn't see that. If f1 is equal to this and f2 is equal to that, right? There may be some expressions that are common to both of those, right? So if we had logic generating b bar d, we don't have to replicate that logic to calculate f2. We can take this one value that we used to calculate f1 and feed it into the OR gate that we're using to generate f2. So if you write product of sum equations for these three functions, f1, f2, f3, you may find some terms in common. Okay, so you can calculate two things. For example, in this example, the solved example, f1 had 1, 2, 3 things it had to calculate. f2 had 2 things. f3 had 3 things, right? But you can share some of these expressions. For example, b ANDed with c is used in both f3 and f1. Okay, so you're just doing some analysis, looking at how many unique terms you have, how many terms you have total, and how many terms you actually share from one expression to another. Okay, and then questions 10 and 11 are related to programmable logic. So question 10, you're making an 8-input device that unlocks when you have any of the following combinations. This particular pattern of 1s and 0s, or this pattern where x means it could be a 1 or a 0 coming in, or this pattern where the x's mean it could be a 1 or a 0. So this is a shorthand way of writing 4-bit patterns. Right? One where both of these are 0, one where they're 0, 1, 1, 0, and 1, 1. This is a shorthand way of writing 4 other bit patterns. So there's a total of 9 combinations that will unlock this, right? Here's one of them, here's 4 more, and here's 4 more. All right, so make a fuse map for a programmable logic array, okay, such as this. And then question 11, you're working with a prom, which is a programmable OR plane and a fixed AND plane. Check the definitions we went over. And so this one, again, you have 8 things and 9 things that will unlock it. 1 here, 4 here, 4 here. And you'd like to show the fuse map for this. Now the fuse map actually has 256 rows to it. Don't show all of those rows, okay? Don't draw the unused rows from the AND plane. Just show the ones that you need. Otherwise, it's a ridiculously huge picture. In these questions, 11 and 10, it's probably good to look at the solved solutions, right? The 10s and 11s. Just to get an idea, what is it talking about? What kinds of things can you do? Because we've only talked about fuse maps once, and it was pretty quick. So go ahead and look at the solved ones to get some insight on that. All right, so that's the homework. Let's talk about multiplexers and demultiplexers. So what's a multiplexer? This is an example of a 2-to-1 multiplexer. It has a pair of inputs, input 0 and input 1. It has a select line and it has an output. And basically the select line chooses which of these inputs should get sent to the output. So if our select input is 0, this circuit basically connects input 0 to the output. Okay, it acts like just a plain old wire where this line is connected to that, and input 1 is ignored. But if you set your select line to 1, then it takes input 1 and sends that to the output, and input 0 is ignored. So it's a switching circuit, right? It has the ability to say, do I want to send my output from input 0 or input 1, right? And you can control which input you're reading from by the select line. Select is 0, select is 1. right? And it routes one of those to the output. That's a basic multiplexer. A demultiplexer does the opposite. A demultiplexer says I have one input, which output do I want to send it to? So if I set my select input to 0, it'll take my input and send it to output Z0. And if I set my input to 1, it'll take my input and send it to output Z1. So it's another kind of steering network, right? We can take this input and we could say, should we send the input to that point or to that point? And you can choose by putting a 0 or a 1 into this select line. Okay, these are really, really useful circuits. You can build entire universes out of just multiplexers and demultiplexers. Okay, they're really good desert island components. So what can we do with these? Well, here's a typical example. Suppose we have an 8-to-1 multiplexer, sometimes just call them MUX. And we have 8 inputs, input 0 through input 7. And now we need to choose one of 8 inputs, so we have a set of select lines, S2, S1, S0. And suppose over here we have a 1 to 8 demux, which takes a single input and sends it to one of 8 outputs. And this also needs 3 select lines. And these are usually called 3 to 8 because you're basically using 3 lines to drive one output. But anyway, just worry about MUX and demux. So this is sending one of 8 input lines to a single output. This is taking one input and sending it to one of 8 output lines. Well, suppose we connect these together, maybe across some great distance, and we have some way of changing these at the same time. So we use a clock, for example, and we start off with all of these set to 0. So what is this circuit doing? It's taking 0, 0, 0 means input 0, and it's sending it to this output. It's coming across this wire to the other side of the country where it feeds a demultiplexer, and since it's selecting 0, 0, 0, that demultiplexer goes to this output. So whatever is on input 0 is now appearing on output 0 over here. Now our very precise clock ticks, and we change our select lines to 0, 0, 1 on both sides, and now input 1 is being sent to this output that's going through this wire, and this wire is being sent to which output? 0, 0, 1, Z1. So now input 1 is going to Z1. And our clock ticks, and we move to select combination 0, 1, 0, that's 2. And now input 2 goes to our wire, goes through the demux, comes out on Z2. And as we do this, what are we doing? We're transmitting parallel data. So input 0 goes to output 0, input 1 goes to output 1, input 2 goes to output 2. We can do this across 100 different wires, but we only have one physical connection between these two systems. We're time multiplexing, okay? And that's a useful thing. It's a way to transfer parallel data across a non-parallel connection. So multiplexers are just inverters with switches. That's a question from somebody. Yeah, multiplexers are pretty easy to build. So, and this, yeah, we got a few minutes left. So we have two inputs, and we have a select line, and we want an output. Alright, if our select line is 0, we want the output to match input 0. So all of these cases up here, the output should match I0. So 0, 1, 0, 1. All of these cases down here, S is 1, the output should match I1. So this column here, so 0, 0, 1, 1. So that's not a bad function to implement. If you k-map it, these two will compress, these two terms will compress, and you get a pretty simple expression. This does relate to inverters, but not directly. But we'll come back to that. We'll see how this ties into basically being an inverter with a switch. So we can build this with traditional logic, right? And we can do the same thing with a demultiplexer. Now, if you wanted a 8 to 1, right, with 8 inputs and 3 select lines, that's a big truth table, right? 8 inputs for those, 3 inputs for those, that's 11 inputs total. That's 2,048 rows in your truth table. Not something you want to write a sum of products for, not something you want to try to make a k-map for. Okay, so let me just show you a trick. Suppose we have a 2 to 1. And suppose we have another 2 to 1. And we have a select line on here. And so we're going to select one of these two inputs to pass to our output, and one of these two inputs to pass to our output. And let's suppose that this is the same select signal. And let me call this, I never know whether to call it S0 or S1. I'm going to call it something later. Okay, let's take these two outputs, put it into another 2 to 1. So this is input 0, input 1. Here's another select line. And here's the output of this. Well, if I make both of these select lines 0, what's going to happen? Input 0 will come into both of these and come out here. And then since this select line is a 0, this top value here will come out. Right? So Z will come from this input up here. If I make my input 0, 1, well, again, the 0 causes I0 to come into both of these and come out here. The 1 here is going to pick this lower value to be selected, and my output's going to be equal to this. So if I call this S0 and S1, and you do this for all combinations, you'll find out this is just a 4 to 1 multiplexer. And if you take a collection of these 4 to 1s and put them together in the same type of structure, you can make an 8 to 1 multiplexer. And if you take a set of 8 to 1s and put those together, you can make a 16 to 1, and so on. So one of the big things we do with multiplexers is we build bigger multiplexers out of them. And that's kind of cool. It's always fun to be meta, right? So we don't need to go down to the truth table, right, and do our sum of products and all that kind of stuff. We can actually use a multiplexer to implement more multiplexers. Let me leave you with one more thing, and we'll talk more about this on Thursday. So here's a 4 to 1. Let me call my output F. And this is I0, I1, I2, I3. Suppose I want to implement some random function. I don't know what, I'll just call it 0, 1, 1, 0. right? I want to build a circuit that does this. I don't need to do sum of products and so on. Here's what I can do. I can just feed these values into the 4 inputs of a multiplexer. And if you look at what a multiplexer does, if my input is 0, 0, this will get sent to the output, f will be 0. If my input is 0, 1, this will get sent to the output, and f will be 1, and so on. So we can build any kind of logic function that we want just by using a multiplexer. So these things are dynamite, right? We'll play around a lot more with these. All right, so the questions on the homework related to multiplexers, there's 2 of those. You might have to hold off on those until Thursday, but take a shot. It'll help you figure out what questions to ask about muxes and demuxes. And we'll continue with this topic on Thursday, and then we'll talk more about other kinds of decoders and other kinds of logic systems. All right, keep going with the labs and the homework. You're doing great. I will see you on Thursday. Have a fantastic rest of the day.
You too.
Thank you.